Hello again. I just did a video where we found this symmedian point with this method of reflecting the median over the bisector. Now I want to show a different method, and I'll try to use the same triangle. And I just realized if I turn this paper over, I can almost see it. Well, I can see it sort of in there. So I'll just draw this triangle. We'll have to do everything again, but let me just say I'm going to draw this triangle. Same one we had before. I have to measure the lengths again, but that's part of the new process. I forgot to time how long the other one was. Okay, so there's the triangle we're dealing with. And now it shouldn't matter. I think you should label the methodology I used assumes that we're labeling the ABCs in a clockwise direction. It may not matter. These are not, you see, the same as before. A and C are reversed, but it's still A, B, C like that. So, but it doesn't matter. That means this side over here is C, this side over here is A, and this side over here is B. And then I need, for this method, I need to measure them. And I'm going to measure this, and I'm getting, 5.9. I almost remember that. So this is 5.9, and then BA, the number A looks like it's 3.7, and then B to C, or this one, which was B, side B, going up there, looks like it's 7.4. Okay, that's what we need. Now we're going to combine plotting and computation. This, by the way, is not an uncommon trick in navigation. If you want to solve a three-body fix, a horizontal section angle, taking three different bearings, A, B, C, like that, and then solve for where you are based on those three measured angles. That's a solution which can be done all plotting, like this can, or you can also do a short computation, and that makes the plotting much faster and more accurate. And this is sort of the same sort of exercise. And but to make it easy, and I'll have a link to this, we just made an app you can put in your phone or something like that, where you just enter these three sides. So side A, what's A is 3.7. Now this is, let's see if I can do this, 3.7. And then B, that's A, B is 7.4. B is 7.4. Are you seeing? Oh yeah, okay, I get this over where you can see it. I didn't stop thinking about that. Okay, sorry. And then C is 5.9. 5.9. Okay, so then it's calculated several things up here for us. Now, it did what's called B to A prime. So this is A, and over here somewhere there's something I'm calling an A prime, which is up here. And this is this distance, and that distance is 1.4. And then we have C to B. See, here's B down here. So somewhere down here there's a B prime. And then C to B prime is 2.0, maybe 2.1, I don't know. And then A, here's C goes up there, so there's somewhere C prime. A to C prime is then 4.7. Okay, then you just plot those out. So if I go here, 1.4 is here. And then I'm going to draw that line from here to there, like that. That's that one. And then this one is 2.1. 2.1 is about here. And then I'm going to draw that line, like that. And then what's the other one? And what's the other one say? It's called A to C prime. Oh, C goes up here, A to C prime is, what did we say? That's 4.7. 4.7, way up there. Okay, 4.7 right here. And then you draw in that line. And then that's your symmedian. Oh, and I don't know if you can see it through the paper or not, but that's where it was before, right? So that's that technique, which takes, I'm talking about it, but that takes just a minute or two to do that. And if you did this with, you can have this app like in your phone or something, or I'll write up a little note on how I calculate these things here. Then you just have that app in your phone, and then you get a micrometer, because on a chart table you'll be measuring these distances with like a micrometer, and then you plug them in, and it's going to show. In other words, you wouldn't just put it right in the middle. If you want to fix, you'd put it over here somewhere. Now, again, let me back up. This whole method that we're discussing now assumes that the uncertainty in this one, uncertainty in that are identical, and that there is no constant error. Like no index correction. We're assuming the index correction is right, etc. No Lubber's line error in the compass. And if that's true, then that's your right answer. Now, our paper, which I think is important, shows that this is not true. This is in fact not true when these uncertainties are different. It moves it around notably. Obviously, if these have big errors and it's a small error, you're going to be on that line somewhere, basically. Well, let it go at that, and then I have a written up blog post that covers this stuff, or it's sort of introduction to what we're doing now.